So the purpose of this video is to demonstrate the correlational analyses. For this, we are considering two continuous variables, one that has been labeled minutes exercise, and the other one is days happy. So the researcher is interested in knowing if a person exercises a certain amount of minutes during a week, will they report a somewhat related number of days happy during a month. Now, science has indicated that there is a relationship between physical activity and mood. In this case, we're simply classifying that mood or qualifying that mood as days happy in a period of a month. The first thing that always like to do, and I encourage you to do, is to explore these variables to make sure that the assumptions of normality are being met, that we do not have influencing cases such as outliers that may cause us to report biased estimates. So I click on Analyze and I click on Descriptive Statistics and I go to the Explore option. I can reset this. Actually, I've already run this once, so in doing so, I already had days happy sitting on the dependent list. So let's bring in the two variables of interest into that box. As I click on statistics here, I'm interested in descriptive statistics, and I'm interested in percentiles because we've already worked with the quartiles, and percentiles will actually give us a measure of the distribution of the data by quartiles, actually by more than quartiles, but you can make a decision about the quartiles within the distribution as the output emerges. So click on continue. And we also want to visually inspect the data. So what I do is I click on normality plots with test. I don't worry about factors because I don't have any factors. If I had a factor, that would be placed actually on the factor box, and the factor box would be a categorical variable such as boys and girls. If I was interested in the differences that exist between boys and girls in my analyses, I would bring in the gender variable into a factor list, and then I would see the distribution of the data by the categories of sex or gender. But since I do not have any factors in this case, I simply leave factors out, and I can click on dependents together, or you can simply click on none, but I do actually want to see the box plots of these dependents and dependent variables. And so let's click on OK, and now let's go ahead and click on OK. So the emerging output tells us that we have 84 cases. 100% of them have been considered. We do not have any missing data. We have a mean of 57.89 for the minutes exercised during a week, and we have a total of a mean 17.71 days. Now that's actually kind of funny because we don't have 17.1 days. This would be rounded up to 18 if the basic measurement unit was days. I'm going to explore very quickly my skewness and my kurtosis. I can see actually that I have a kurtosis issue and I have a skewness issue. Now for kurtosis I can correct, for skewness I can as well, but skewness mostly will be the problematic situation that we have within these variables. I look at skewness for days happy and it appears to be normally distributed. I can look at my percentiles and make a decision about the distribution of the data by quartiles, so the 25th percentile, the 50th percentile, the 75th percentile, and of course the rest. My test for normality, because this is a relatively large sample, at least over 30, I will be looking at the Kolmogorov-Smirnov test, and it's quite evident that these are significantly different from the normal distribution, as the significance box right here indicates that this is smaller than the 0.05 level that is declared within this analysis. If I visually inspect the data, I can see that we have a problem here. If I double click on this and I insert a normal curve into it, I can simply close on this and then close, and then the normal distribution or the normal curve is placed over the graph. I can see that this is actually negatively skewed. I have a large body of data towards the left, and this opens up stretching over to the right, where anything and everything above 100 appears to be in a problematic area of about 2 standard deviations from the mean. And so, with 140 being an influential case and really pulling our mean up. So as a researcher, I can make a decision to delete this point, or actually all 3 of these points, anything from above 120, and see if that improves. However, let's say that I don't want to do that. If I insert a normal curve over this graph and simply close out of this, you can see that this is somewhat evenly distributed as the majority of the data falls within the normal distribution. The tips are actually cut off here, but we don't see anything that's on the extreme areas of the normal distribution. Now there's one problem with this normal curve right here. It's a little bit flat. So I'm thinking that this is kurtosis. So if I go back and I not analyze, but I've already analyzed this. If I look at days happy, I can see that we do actually have an issue of a flat variable here, relatively flat as well. Actually not flat here, but actually pretty pointed right here on the minutes exercised. So beyond that, I could simply put some haste into this and run the analysis for the correlation, or I could be a little bit more cautious and come down here and look at influential values. And so this is telling me that 8, 9, 21 are problematic. And if I went into my data, let's see, I clicked on this and went back over to my data and I looked for those cases. Number 6, okay, I can see what's going on. Which one else was it? 9, 21. They should actually be pretty large values. So 9 is 124. 21, let's look for 21 at 121. Again, these are influencing cases that appear to be outside of the distribution, outside of the normal distribution. Now you can simply click on this and delete, but we're not going to do that. What we're going to do is we're going to try to keep all the data within this data set, and actually before we run our analysis, we're going to create some transformations. Let's reset this right here. Let's bring in minutes of exercise into a transformation. To do so, I'm going to type new minutes, and I'll actually conduct 2 transformations that the book recommends for cases when you have skewness. One is going to be a square root transformation, and now I can insert minutes exercised and click simply on OK. And if I look at my output, all the output says, don't be alarmed, all the output says is, hey, listen, you have computed a new variable, which is called new minutes, which is a square root transformation for minutes exercised, and you've executed that. If you look at your data output, you should have a new minutes variable. And because I don't know exactly yet where this stands, I'm going to actually create a new transformation for the data, and I'm going to call this new minutes 2. And I'm going to do a log 10 transformation on this one, again recommended by your book for correcting issues of skewness. So a log 10 transformation, and I'll bring in minutes exercised again, and I'll simply click OK. And now if I look at the data, I know that I have new minutes and new minutes 2. So let's go back to analyzing these variables for normality, which is something that we should be doing every time we're running analyses. Now, for some reason with correlation, sometimes you can simply run your correlation analyses, and well, not sometimes, but you can simply run your correlation analyses, and because there's a Fisher's correction that correlation does for us on SPSS, we can interpret very easily without necessarily worrying too much about normality. But because we have said in class this is important for us, I would like you to consider that. So we already know that statistics, we already picked these statistics, and we also have everything for the plots that we want to create. So simply click OK, and let's look at the data now. So now what we're looking for is days happy, which we said was pretty normal in terms of skewness, the rule of thumb of less than 1. If you divided the skewness statistic by the standard error, you would see that this falls well within the standardized scores of less than 1.96 plus or minus. And now we can look at new minutes and see if we've actually improved that variable. So new minutes now is 1.48, and in the new minutes 2 with a log transformation, we are now below the 1, the rule of thumb of a 1 for skewness. And so I'm going to make a decision to run my correlational analyses with new minutes 2 and days happy. So the next step is to actually, if you wanted to, you can look at your Smirnov-Kolmogorov test, and you can see that they are still significant in terms of a normal distribution. You can see that these have corrected a little bit. If you were to insert your normal curve on this because you really wanted to see it, then you would still see that, you know, these guys that were sitting way outside of the normal distribution now are at the very tip of them as the extremes. And if you look at the curves, normal QQ plots, you can see that you have a nice curve that's zigzagging this line. You have for new minutes, you actually have these data points that are very far away from the hypothesized normal distribution. And when you look at this one, these points are actually starting to get up on line, and these are not so far. And this again is a visual inspection. When you pair your visual inspection along with your statistical computations, particularly the Smirnov-Kolmogorov test, then you can make a decision. We're simply going to run the correlational analysis now by clicking on Analyze, click on Correlate Bivariate. This is bivariate correlation. Let's go ahead and reset this. Then we're going to bring in the variables of days happy and new minutes 2, which was our most normally distributed variable that we computed by transforming the data. We're going to run a Pearson's correlation because these are two continuous variables. We don't have any rank order data. And we are simply declaring a test of significance with two tails because all we're looking for is there a relationship between this? We have not declared is a relation positive or negative, or does it have a certain direction on it? This is not a directional test. This is simply a two-tailed test, and we click on options, and maybe you'd like to see the means and standard deviations, and click on continue. And I said maybe this is not necessary, but I think it's always interesting to make a decision about the data, how well the data has been distributed in this analysis. So let's go ahead and click on OK, and let's look at the output box. So when I look at the output box, I can see that I have days happy, a mean of 17.71. That has not changed, and the standard deviation is 6. We have a new minutes mean of 1.74. Now this is tricky because this is log transformation, and interpreting this right here could be problematic. But not necessarily so, because in a correlational analysis, we're not trying to make an inference. We're simply deciding whether there's a relationship between these two variables. And when we look at our correlation analyses, we can see that the Pearson correlation for days happy and new minutes is a 0.505. There are two asterisks on this value. This is actually called the correlation coefficient that indicate that this is significant at the 0.01 level. And that would be it. Now, just for fun, let's click on Analyze and run a correlation with the original variable to see how different the original variable would have been and if we would have had a problem with running that analysis. So let's click on OK, and let's look at what emerges here. If you notice, we have 0.50 on the previous and a 0.51 on the original data, which is not terribly different. Of course, we're eyeballing this and making that decision, but it's not terribly different from the original one, which again suggests that through a Fisher's test and correction for normality, your coefficients can be interpreted if you have some errors of normality in your data. So that concludes our presentation on the correlational analyses, and now we're going to run that on Excel as well.